Hi, everybody. Welcome back. This is chapter 11. We're going to be talking about physical and chemical control of microbes. These are our learning outcomes for the chapter again. So we're talking about controlling microbes. Historically, we've used salt, smoking the food, pickling the food and drying it, and all these things to try to control microbial growth on, let's say, food or something that we're trying to store, but also by burning clothing and corpses, trying to eliminate the contamination associated with those things as well, so they don't contaminate like our livelihood outside of that. And we also used containers that tend to be antimicrobial just naturally. So the four main terms that are going to be involved that we're going to be using to describe microbial control will be sterilization, disinfection, antisepsis, which you can also call degermination, and then decontamination, which is sanitization. And sterilization is going to be the destruction of all microbial life. This is including endospores. Disinfection, we're talking about most microbial life, usually on inanimate surfaces. Antisepsis is the same thing as disinfection, but this time for animate objects, so living surfaces. And then decontamination or sanitization is mechanical removal, so like actually actively physically removing something from microbes from an inanimate or inanimate surface. So sorry, my hair keeps getting in my face. So this chart is an excellent resource for you guys whenever you're coming back to study for chapter 11 and you're wanting to keep, everything in a nice set place. What can sterilize, what can't, what is used for disinfection, what is used for antisepsis, and so on and so forth. This chart really breaks it down, I feel like, in a really usable way. So I would refer back to this for future purposes, but we're going to go through each of these in the chapter. So microorganisms obviously can cause spoilage of food products. A lot of times our environment around us has just a mixture of microbes and not just any specific one in this area and then one in that area. So a lot of this stuff can include vegetative and endospores, fungal hyphae and their spores, the yeast, the protozoa, the trophozoite versions and the cyst versions of the protozoa, and the worms, viruses, and prions. All of this sort of stuff can be all over in our environment around us. The ones that are the most resistant to being gotten rid of, essentially, are going to be the prions, because they're just proteins. So that's the only thing that you would have to be getting rid of, but it's hard to get rid of those misfolded proteins because they want to stay misfolded proteins. So in order to truly denature them and get rid of them, you usually have to do it much higher heat than usual, or treat them with sodium hydroxide that will help denature the actual hydrogen bonds that are going on in the proteins. But anyways, after that, as far as the microbes go, the endospores, of course, are going to be the hardiest of all of these. Then the mycobacterium, which makes sense when we talk about waxy coating on them. Staphylococcus and the Pseudomonas. Remember, the Staphylococcus are going to be really resistant to like salt and stuff like that. So they are going to be a little bit hardier. You can just go on down the line. You can see that the most susceptible would be the enveloped viruses, but don't let that trick you, because that doesn't mean that they get on a surface and then they die really easily. This is going to include, it says in the little note down at the bottom, this is going to include COVID. So COVID is an enveloped virus, so it's still no joke. These are still going to pose a threat, even if they are the least resistant to these means of getting rid of them. So endospores are the most resistant. The goal is to destroy them, right, completely. So that will help us remove any sign of that organism from ever returning. And usually if it's going to kill an endospore, it will kill everything else. So that's the idea. That's usually the goal of most of this treatment, is to remove endospores in general. All right, sterilization, again, removing everything, all viable organisms. This includes endospores. So any material that has been subjected to this process is referred to as sterile. And those sterilized products are essential to human well-being, especially when we're talking about having surgery. You don't want there to be even any endospores on any of the equipment that your surgeon is using. Syringes that might be used in the medical field, and certain packaged foods, we want to avoid those having any microbes on them. So when we are talking about disinfection and disinfectants, we're going to be destroying mostly the vegetative pathogens, but not as much the endospores. So these are usually used on inanimate objects. where it's not as important to get rid of endospores, but you just need things as clean as possible within a certain like amount of time or something like that. You can't treat everything to be sterilized because it usually takes time and quite a bit of like energy to put into destroying a lot of things. So antisepsis, this is a controlling growth of microbes on blood, on tissues like skin. Asepsis is a practice that prevents entry of infectious antigens and agents. That's what I meant to say, sorry. Asepsis is a practice that prevents entry of infectious agents into sterile tissues and prevents infection, therefore. The aseptic techniques like we use in the laboratory, these are going to be as sterile as possible, so sterile methods to exclude all microbes. We don't want to be passing anything back into our culture or anything from our culture back out into the environment. Antisepsis would be any application of chemical agents that would aid in something like this. So we are talking about exposed body surfaces, wounds, surgical incisions. These are going to be things that will destroy or inhibit vegetative pathogens on living tissues. Okay, we're talking about cidal versus static. All right, cidal agents. Anything that ends in side or cidal. Think of homicide. Think of that. That's going to be killing, okay? Germicide and microbicides are things that kill microorganisms in general. Bactericide, they kill bacteria, usually not including the endospores here, okay? So bactericides, we're talking about the vegetative forms. Fungicides, we're killing fungal spores, hyphae and yeasts, anything related to the fungi. Virucides will inactivate, or like what we would say kill, but they're not alive, right? So inactivating viruses, especially in the living tissue. And then sporicides, these are able to kill the endospore forms. So static agents, when we talk about static versus cidal, right? So cidal will be killing, and then the static is going to prevent growth or stop the growth of these organisms. So microbes will be prevented from multiplying, but they won't be killed. They'll be stopped, but they won't be killed. Bacteriostatic agents prevent the growth of bacteria on tissues or in the environment. Fungostatic chemicals inhibit fungal growth, and then microbostatic for any microbes in general. Decontamination is any cleansing technique that mechanically removes microbes and debris. This would include like scrubbing with a scrub. The actual scrubbing action itself, that would be the decontamination aspect of it. So a sanitizer is a soap or detergent that would be used to sanitize. And so that's the decontamination, mechanical removal of something. So when you're trying to determine what you should be using to remove microbes, these are the questions that you want to ask yourself. Does it require sterilization or not? Can it be reused? Do we need to be able to re-sterilize it? Does it resist heat and pressure, radiation? What about if we keep applying moisture to it? Will it rust or something like that? Will it degrade? Will it be suitable for whatever application? Because there's some things that can sterilize that you can't do to every single surface ever. Will the agent penetrate to the necessary extent? And is it efficient and safe and all of that? So our critical medical devices are the ones that we would be coming into contact with sterile tissues for sure. So doing surgery within someone's body. Semi-critical medical devices, here we're coming into contact with mucosal membranes. So this could be something like a ventilator or something like that. Non-critical medical devices, these don't touch the skin, don't touch the patient directly, or only expected to touch intact skin. So that could be like the bed surface, for example. So death of microbes. How do we know if a microbe is dead? We've talked about this in previous chapters, that you would have to, plate them out and see if they are still growing cells in there. You can't necessarily judge based on the turbidity or cloudiness of a culture. And even like, how do you determine this based on a surface that you're trying to treat with something? That's even more difficult, right? So so trying to determine whether or not this procedure or whether or not this chemical is going to completely kill off any microbes, that's something that somebody else has to have determined before us through various methods that would be similar to what we had talked about in previous chapters, talking about viable cell counts and things like that. So here are some things that can affect the death rate of microbes, how many of them there are. the nature of them in their population, the type of microbial growth, are we talking about, biofilm, for example, temperature and pH of the environment, concentration of the agent, mode of action of the agent, presence of any solvents, interfering organic matter, and inhibitors. So remember that all chemicals can be affected by pH in their environment, not just organic ones. So, don't forget about that. So here we are looking at measuring the effectiveness of some, microbial agents, antimicrobial agents, with regard to their time and whether or not we started with, a high load of cells or a high microbial load versus a low load, and see how low load is going to get to zero faster than the high load would. Obviously, that sort of stuff makes sense. Yeah. So the actual agent and how it acts on that specific organism, the actual type of the microbe that we're talking about, if we're talking about like endospores versus the vegetative form of those cells, it's going to take longer to get rid of those endospores if you even can with that agent. And then how much time you're putting into trying to sterilize or exposing that pathogen to that agent. So how do they work? Basically, there's four main things that they can target. They can target the cell wall, the cytoplasmic membrane, the cellular synthetic processes that includes RNA and DNA synthesis, and then the proteins. So let's get into this. Things that are going to cause damage to the cell wall, we can have blocking of the synthesis of the cell wall, actually breaking it down. And then it can actually become relatively fragile and lysed due to addition of some of these agents when we're damaging the actual cell wall. Detergents and alcohols are pretty good at disrupting the cell wall. Disrupting the cell membrane. So if we can affect the actual cell membrane and break into, like with that the phospholipid bilayer, right? That can cause loss of that selective permeability. Now things can move in and out of the cell with uncontrolled, right? We'll have loss of vital molecules from within the cell leaking out, and this will allow entry of damaging chemicals that could be more harmful than even that substance that's allowing us to get in. Surfactants are polar molecules with hydrophilic and hydrophobic regions that basically act like a phospholipid. They look a lot like a phospholipid. Remember, we had phospholipids and they had this sort of situation where we have the polar head and the hydrophobic tail. Well, essentially, that's what I wanted to have happen. Essentially, what will happen is with a surfactant, imagine that they also look like that a little bit, and then they can squeeze in between. And whenever they do squeeze in between, that can poke holes into that lipid bilayer and causing things to leak out and allow things to come in before treating them. So this is just a better picture of what I was trying to draw of that happening. So our surfactant molecule going in and mimicking essentially what we would see going on the phospholipids and allowing them to squeeze in between them as a result. And that would lead to weakening of the membrane and things getting in and out of the cell. Microbial cells depend on orderly and continuous supply of proteins, of course. So if we can inhibit all that, just like any other living cells, as well as inhibiting synthesis of DNA and RNA production, then the cell can't function and can't reproduce or anything like that. So that becomes a usable way of stopping the growth of these organisms as well. So we talk about a protein. We have the native state, which is the normal functional state of that protein, and then a denatured form. And denatured is a disruption of the protein, usually due to breaking of hydrogen bonds that are going to be naturally going on within the shape of that protein that provides the protein with its functional shape. And so, we can disturb that somehow with heat or pH or something, and then cause that protein to no longer have its functional shape and ability to perform its job. And that's the idea of denaturation of those proteins. The best way to do this often is the use of moist heat. So this is going to cause irreversible denaturation of the proteins. And that's what you see happening when you cook an egg. So when you cook eggs and you get them hard boiled, or if you are cooking them on stovetop, doesn't matter. And you see that, egg white, it was liquidy, clearish, and now it is, hard, solid. You can't go back, right? Have you ever tried? Because you can't, by the way, because you've denatured those proteins that are in there, and you can't revert back to the original, natural state, the native state. So strong organic solvents, we have moist heat, and we have strong organic solvents that are able to have this effect. And also phenolates can have this effect as well. Other effects that we can see on protein are metallic ions binding to the active site so that our substrates can't interact with the proteins anymore. So that keeps it from being able to function. So remember, with our proteins, we will have in our native state, our substrate combined in one site. I don't know why this has two different substrate sites, but whatever, I'm not going to argue with it. Combined in one site, and then that can lead to, changing that substrate into the product, right? Well, when we have denaturation, this is the shape of the protein now, and it can no longer interact appropriately, and that blocks the function of that molecule. So heat is the most widely used method of microbial control. Other methods will include radiation, filtration, ultrasonic waves, which we're not going to talk about really, and then cold, not useful really. Okay, you're really not going to kill anything with cold, just FYI. Nothing dies from the cold. Hot water, well, there are some microbes, don't want to mislead you here. There are some microbes that will die from the cold, but it's not an effective and reliable way of controlling microbes. You can slow them from growing, stop them from growing, but then they're going to live when you get them out. So I just don't want you guys to think that you can put your steak in the freezer and when you get it out, there's no bacteria. Those bacteria that were on it before are just going to come back to life, generally speaking. So just, don't rely on that to get rid of microbes, because that's not how cold works. Okay, so moist heat, we're talking about hot water, boiling water, and steam, those sorts of situations. Temperature will range anywhere from 60 to 135 degrees Celsius, depending on what we're trying to do. The temperature can be regulated by adjusting pressure in a closed container, and that allows that basically for everything to happen a little bit faster, a little bit more controlled environment. So this will operate at low temperatures and short exposure times compared to dry heat, which is significantly different. So we have in dry heat, we have air with low moisture. I mean, you know what dry heat is. This is going to include incineration. So burning things, cooking things in an oven, that's dry heat. So this is going to dehydrate the cell. Loss of that water increases the stability of some proteins. So that's why we have to have higher temperatures in order to denature the proteins, because you're taking the water out, stabilizing a protein, but you still want to get rid of that organism. You don't want to stabilize that organism's proteins because you're going to keep it around. So you want to kill it now. So you're going to have higher temperatures in order to get rid of it. And that's why dry heat requires higher temperatures. So it helps the denaturation process to have moisture in there. Okay, so here's the difference. So if I take something at 121 degrees Celsius and I'm applying moist heat, then that will allow us to sterilize within 15 minutes. If I take something that is at 121 degrees Celsius with the dry heat, then we can sterilize that within 600 minutes. That's 10 hours, folks. That's completely different. You see the difference here. So this is no small difference. This is a massive, massive difference. And this is why you have to burn things to ash to get rid of them appropriately when we're talking about dry heat, typically. So heat resistance, bacterial endospores have great resistance, of course, we talked about that. Destruction usually requires temperatures above boiling. These guys can survive being boiled, okay? Resistance of each endospore and each vegetative cell, it just depends on the organism, the cell. High temperatures allow for shorter exposure times, of course, and then lower temperatures require longer, no matter if we're talking about moist heat or dry heat. Thermal death time is a term that refers to the shortest length of time required to kill all microbes in the test at a specified temperature. So if you're putting 121 degrees Celsius and you're trying this new method of killing things out, and you pop it into that new method, what's the shortest amount of time that has to go by in order to kill everything in that test? Whereas the thermal death point, this is the lowest temperature that's required to kill all microbes in a sample in 10 minutes. So you have 10 minutes to kill every single microbe in your new little setup over here. What is the lowest temperature that you have to put it at, the absolute lowest but you'll have to put it out to still kill everything in the sample within 10 minutes. So that's the idea there with the thermal death point. With boiling water, we can use this for disinfection, but you will not use this for sterilization. It doesn't kill everything. We've already talked about how endospores can live through that. So resistant cells won't be destroyed. We do, if you are going to be boiling in order to disinfect something, then we would recommend 30 minutes to kill most non-endospore forming pathogens. This can be easily recontaminated whenever you are removed from the water. You know, you cool back down and instantly get recontaminated from the environment. So that's a problem there. But this is useful for home disinfection of water or for materials for babies. If we need it clean enough, we need to cleaning food and utensils and bedding and clothing from people who might be ill, that sort of thing. Pasteurization, here we're just going to be either flash or batch method, moving from hot temperature to cool temperature. You go to hot for a certain amount of time, and then you cool down for a certain amount of time. And then you go to hot for a certain amount of time, and then you cool down for a certain amount of time. And you do that over and over and over again, and that will help you remove pathogens while retaining that liquid's properties and flavor, like what we have from milk, but you will not sterilize. Pasteurization does not sterilize. It will inactivate most viruses and destroy vegetative stages of about 99% of bacteria and fungi. Right, so we use this for milk, wine, beer, and other beverages, which most of us are aware of. To sterilize something, a lot of times, so if we're going to be using moist heat, which is the best one, right? So that's if you can use it. The most commonly used method for using moist heat to sterilize something would be using an autoclave, and it uses a lot of high pressure to get us to that temperature that we're looking for, that 121 degrees Celsius. So 15 pounds per square inch, which will get us to 121 degrees Celsius. And then we can cook something for 20 minutes in that setup with moisture in there. And that will allow us to sterilize within that 20 minutes, okay? That's the idea. So we can use this for heat resistant materials. This will be glassware, cloth, certain metal instruments, liquids, and other things. And there will be some heat resistant plastics as well that can go through this. It just depends, but this can be quite degrading to certain materials. So you can't always use this on everything. Additionally, it has to touch the surface in order to sterilize it. So if it can't get inside of something, that inside part will not be sterilized. So it has to be touched by that moisture, that steam, in order for it to actually work. So this is just the setup of an autoclave, and essentially how it would work, but we're just injecting steam into a pressurized chamber and then heating it up to sterilize. So dry methods, this includes incineration. This is like what we do in the lab with our loops. So literally burning things off, right? So this would be Bunsen burner gets 1870 degrees Celsius at its hottest point. And furnaces or incinerators that are made specifically for incineration, those guys will operate anywhere from 800 up to 6,500 degrees Celsius. So very hot temperatures. This will ignite, literally burn the thing to ash. That's what the goal is here. So we can only use this really on certain metals and heat resistant glassware, right? Because it gets so hot. Hot air ovens, this works exactly like your oven at home. I don't know what to tell you about it other than that. Like, we're going to try to sterilize things by cooking it in an oven for like 4 hours. That's essentially what's going to be going on here. But it does use dry heat. So anything that can't be exposed to moisture can be put through this process. All right, cold. Some microbes are killed by the cold. Very few of them are, though. Most are not killed by the cold. They're not adversely affected by cold at all. Long-term refrigeration, gradual cooling, deep freezing, not affected. So freezing temperature is not a good way to eliminate things, but you can stop the growth of certain things to preserve things if you don't want to eat it right away, for example. So psychrophiles are organisms that, remember, can grow at freezing temperature. So they can also continue to secrete their products, which can be toxic at those temperatures as well. So just keep that in mind, and not everything is safe in the cold. Desiccation is just drying something out. Some pathogens can actually be preserved themselves upon desiccation. It's not a very reliable way of killing off microbes on the surface of food, for example. Yeah. Lyophilization is just a term of referring to freeze drying, literally. So you are at freezing temperature, sucking the moisture out of something, drying it out. And then that helps to preserve. A lot of times we use this for preserving certain cultures. So if you have like a pure stock of a culture and you want to keep it for later, then you can lyophilize and then use it to rehydrate it later on and then regrow that sample, which is where all of your cultures come from in the laboratory. That's where I get all of them from. I have lyophilized samples that I buy from other companies, and then I rehydrate them and then grow them out for you guys. So that's where those come from. This actually method that is used quite often as far as preserving like medications and stuff like that. If you ever have to inject like a saline into a powder and then rehydrate it, that's what it was. It was lyophilized, that powder. Okay, radiation is also useful for microbial control. Radiation, we are talking about basically high energy molecules, right? So we're going to emit atomic activities, okay, energy emitted from atomic activities and dispersed at high velocity through matter or space. So it's more important, I feel like, for you guys to understand the two versions of these kinds of radiation. We have ionizing and non-ionizing, okay? So when you irradiate something, we are bombarding it with radiation. So that would just mean exposing it to something that acts radioactively to cause damage that radioactive things can cause, either via ionizing or via non-ionizing radiation. So ionizing is the worst of them. It's going to cause the most damage, and you have to have very special barriers to block it. Most barriers that you might put up, definitely not glass. Most barriers are not going to impede the movement of those radioactive particles. Sometimes even lead itself can't impede the movement of these particles. Depends on the particle. And then we are talking about non-ionizing, where we have abnormal DNA bonds forming, and that's going to be causing mutations in the DNA. So ionizing radiation, it can sterilize without any heat. We call this cold sterilization. This will allow us to sterilize heat-sensitive materials, any heat-sensitive materials. So devices that can emit ionizing rays. We have gamma ray machines, we have X-ray machines, and we have cathode ray machines. Ionizing radiation is radiation that ejects orbital electrons, so electrons in the outer orbitals, from the actual atoms, making part of whatever element that you're using as radioactive, and then that'll cause ions to form. We can eject those electrons and break apart the bonds of whatever thing that we're exposing it to, including cause damage to the proteins, including bacteria that we're treating, right? So that's how that would happen, and cause damage to those, because we're going to be ejecting the electrons from the actual bacterial atoms, and then causing ions to form in them as a result of the bombardment with the radiation from the ionizing radiation. For non-ionizing radiation, we have UV rays, and that's literally going to just energize the state of the atoms in the DNA or whatever it is. So we'll have abnormal formation of bonds within molecules such as DNA that can lead to mutations later on. So the effective, if you're going to be using UV radiation, 240 to 280 nanometers, peak at 260. We have lamps that are going to basically be optimized for this to help treat surfaces. So this is not as penetrating as ionizing radiation, and we do not necessarily consider UV radiation for sterilization. We don't think it's particularly useful for that. So we will disinfect things with this. All right, we have formation of pyrimidine or thymine dimers. Basically, those pyrimidine dimers are going to cause bonds between the T's that are next to each other instead of the T to the A across from each other, right? So this is how it should be, and it isn't. And then UV light causes this to happen here. And now whenever we go back to make copies of our DNA when we're growing cells, they will not grow properly. They'll have the mutations there, and we'll have to, this can, but yeah, so the mutations will allow the cells to, it won't be able to divide properly, is what I'm trying to say. Okay, that can lead to inhibition of growth and cell death. UV radiation can also lead to free radicals and toxic photochemical products. These will interfere with cell processes, and yeah, so you can use this for treating non-porous surfaces like glass or floors and the inside of hoods, where we sometimes work with dangerous organisms. Okay, so filtration, you can filter out things if you have small enough pores in your filter. You can actually filter something so that it can be sterile. So this can be used for sterilization. So this is a mechanical removal of microbes using that. So just depends on how, like I said, how fine your pores are in whatever filter material that you are using. You are going to be trapping the right things. You can use this for liquids that cannot withstand any heat. It's important for water purification, obviously. We'll talk about that whenever we get into talking about water treatment. Yeah. We also use it for removing airborne contaminants like HEPA filters, right? So osmotic pressure, this is just talking about salt, using like packing something in salt or even packing something in sugar. So that counts as well. Either way, what happens is it sucks the moisture out of the cell, right? Due to that hypertonic environment around it, right? That'll lead to plasmolysis in the bacteria, and then it's not good. They'll either die or the bacteria can't grow anymore. So some bacteria are, going to grow fine with that, the halophiles, right? So antimicrobial chemicals. Now we're moving on to the chemical control. They can be in the form of a solid, liquid, or a gaseous form, but most of them are going to be turned into a water in order for us to work with hot water, a liquid for us to work with them. Aqueous solutions, that term means it's been using the water as solvent, and tinctures, that means we're using alcohol as a solvent. We want our chemicals to be able to act in very low concentration. So these are the things that you want to consider if you're trying to design a chemical or choose a chemical or whatever for treating whatever surface that you're trying to treat to remove microbes. You want to be active in low concentrations and soluble in water or alcohol, because that's what we have for the other things. Broad spectrum of functionality. We want to be able to penetrate inanimate surfaces and sustain hopefully a cumulative or persistent action. Resistant to being inactivated by organic matter, things like pus and blood or something interfering with its ability to function. Non-corrosive or non-staining properties of it, and then sanitizing and affordable and all that. Preferably smell nice too, right? So these guys are the high-level germicides. These guys will kill endospores, so it should be able to sterilize if you are using them properly. We'll use these on our critical items that we can't heat sterilize. So our catheters, our heart-lung equipments, and our implants, anything like that that we can't put into heat. Then our intermediate level, you don't need to kill the bacterial spores, but you want to consider, you can't kill the spores, but you want to kill as much as possible. So this would include respiratory equipment and thermometers. Then for low-level germicides, you're going to be using things that can kill only vegetative bacteria, only vegetative fungal cells, some viruses. So these are significantly less effective than the other two. So these will be used to clean things like electrodes or straps or furniture that touches the skin, but not the mucous membranes. So now we want to think about what we are trying to treat. Are we, what microbe is it, the nature of material we're treating, degree of how much it will be contaminated, how much time we have to expose it to whatever cleaner we have, and the strength of that germicide in general. So the germicides are basically going to target similar things to what the physical ones are going to be targeting. So these will be targeting proteins, nucleic acids, cell walls, and membranes again. The halogens or halogens, this includes fluorine, bromine, chlorine, and iodine type molecules. These are microbicidal and sporicidal, so it can be used to sterilize if used properly. These are active ingredients, about 1/3 of all antimicrobial chemicals that are being used. So in 2020, chlorine was one of the main chemicals recommended by the WHO for cleaning and disinfecting surfaces for COVID-19 exposure. So we're talking about bleach here. Yeah. All right, so let's talk about chlorine first. So target microbes, they can slowly kill endospores, so they can kill endospores and will destroy all other microbes. So if it's left there long enough, it can be used to sterilize. Forms that we usually see are liquid and gaseous chlorine. Hypochlorites and chloramines are also used as well. I don't know if you know this, but bleach is sodium hypochlorite. So there you go. Mode of action. Whenever this is in solution, the compounds combine with water. They release something called hypochlorous acid, and then they will denature enzymes permanently and suspend metabolic reactions. So that's what will happen whenever we put this in solution with water. The limitations of this, it's going to be less effective if it's exposed to light. Also, it will be less effective if it is exposed to alkaline pH. Remember, pH is very important for the function of a lot of these molecules, especially when we're talking about acids. And then the excess organic matter can also make it less effective. So indications for use of this, we use this for disinfecting drinking water. This is how we pump chlorine gas essentially into drinking water to decontaminate it. Then we have treating of sewage and wastewater. The hypochlorites, these are going to be used in healthcare to treat wounds, disinfect bedding, and instruments to sanitize food equipment, and in restaurants, pools, and spas. We know how common the hypochlorites are. That's the bleach, right? And then chloramines are used for treating drinking water and certain wounds. Microbes, this will slowly kill endospores and destroy all others. We have, oh, right, so this is iodine now. I wasn't even paying attention, I was just cranking right along. So iodine is gonna go the same, treat the same sort of stuff as the chlorine will, as far as it'll slowly kill endospores and destroy all other microbes. Pretty similar here. We have free iodine that can be in solution, so the I2, and then the iodophores, which are complexes of iodine and alcohol, so tincture, if you will. The way they act is by penetrating the cells and interfere with the metabolic functions of the cells. So hydrogen and disulfide bonding of proteins will be affected by the presence of the iodine. It can be irritating to skin, and iodophores were banned in consumer products in 2017. So you can't necessarily buy iodophore type products now over the counter. So these have been replaced in medical antisepsis because they are, you know, these guys, they're the orangey brown color. Yes. So that is going to be what something that can cause significant staining on your clothing, on skin, on everything like that. So they try to replace these with other things. So, so this is betadine, this is povidone, iodine, and isodyne. Any of that stuff, if you've ever seen the brown fluid like scrubbed onto someone's arm to start an IV or something like that because they are allergic to chlorhexidine, then that's what this is talking about. Okay, so it's very, very dark color. So we try not to use just because we don't have to really as much anymore. But you can be allergic to chlorhexidine. You can also be allergic to iodine, though, FYI. All right, carbolic acid. Carbolic acid, also known as phenol. This is the stuff that whenever we were doing acid fast stains, smells like the chloroseptic. So chloroseptic throat spray. This is phenol. I like the smell of it. So this will target some bacteria, viruses, and fungi. Not everything's going to get killed by this necessarily. It's derived from distillation of coal tar and has certain aromatic rings associated with how it will function. Basically, in high concentrations, they will disrupt cell walls and membranes and proteins. In lower concentrations, they inactivate enzymes and systems in general. So these are limited. They are toxic. Yes, this is not really friendly for like skin applications. They can be toxic at the more effective concentrations. And they were banned in consumer products, including in 2017, including triclosan and triclocarban, which both of those are phenol-based molecules. So it is, okay, so phenol, it is pretty effective as far as what we might be using it for, as far as whenever you need to use this. I'm trying to say this. It's ridiculous. Okay, phenol. Let's just try to read this one. Phenol remains one standard against which other less toxic phenolic disinfectants are rated. The phenol coefficient quantitatively compares a chemical's antimicrobial properties to those of phenol. What I'm trying to say here, phenol is an effective chemical agent to use to control microbes, but because it is toxic, we are trying to develop things that could be related to phenol, which are our phenolics, or that function kind of similarly, but we compare them back to phenol because it's hard to, meet that standard, essentially. That's what that's saying. So, yeah, so we only use these in certain cases now. And it is called carbolic acid. So this was originally used by Joseph Lister as the surgical germicide to treat surgical instruments and surgery areas to make them to kill microbes in those areas, to make it more sterile for surgeries. And it worked quite well. That's very irritating. It's got very bad side effects. So phenolics are basically made based off of phenol. They are different structure, but they work pretty similarly as far as action. Some of these guys will have detergent action as well, so they can help break up these cell membranes and such. And they can act in the presence of certain organic matter. So triclosan is a phenolic, so we don't really use this much anymore. Dichlorophenoxyphenol is the original chemical name for this. It was found in way too many areas as far as like in the environment. So it was everywhere in the environment. It was also causing drug resistance. So that was being an issue. So now we don't really use this as much except for in healthcare settings. For chlorhexidine is another one of these. So if you've ever used Hibiclens or Hibitane or Paradex, Hibiclens is probably the one that you'd be most familiar with. That is chlorhexidine based cleaner. And that is a phenolic, essentially. So we use this for surgical scrubs, for hand scrubbing, other things. You can also use chlorhexidine in the form of like a swab onto like people's arms to prep for IV lines or blood donation and things like that. All right, so chlorhexidine itself will be targeting bacteria, viruses, and fungi. It has complex organic base containing chlorine and two phenolic rings. It acts by causing selective permeability in the actual cell itself, and then it can go into the cell and then cause denaturation of the proteins within. Then, so effects on viruses and fungi are kind of variable. It's better used for bacterial preventions. We use this in hand scrubbing and surgical preps in moderate to high concentration. It is bactericidal for gram-positive and gram-negative, but it is inactive against endospores. And it is mild, it's low toxicity, has rapid action. It is not absorbed deeper to cause any more issues deeper in the tissues, and it can be sold in mouthwashes as well. So alcohol. So alcohol will target most bacteria, viruses, and fungi pretty much. You'll see. There are a lot of different forms, but we will talk most about ethyl alcohol and isopropyl alcohol. Ethyl alcohol is drinking alcohol, but we do use it as medical treatment as well. So concentrations of 50% alcohol and higher dissolve membrane lipids. So that will disrupt surface tension of the cell and compromise the membrane integrity of the cell. It evaporates quickly, we know this, and the vapors can affect the nervous system. So really just those two, isopropyl and ethyl, are appropriate for medical use. So usually water is needed in order for proteins to coagulate. You have to have water present. So you can't have 100% alcohol. So what you want to have is about 70% alcohol so that there's enough water in there to allow for that protein coagulation and essentially denaturation of those proteins due to the presence of that alcohol. So 100% alcohol will dehydrate the cell and inhibit their growth, but not be a protein coagulant. So that's what you want to have closer to 70%. So when we are using ethyl alcohol, this is a skin degerming and disinfectant for some medical equipment. Because it evaporates quickly, we don't want to use it on everything. Hand sanitizers have 60 to 70%. So they are more resistant to evaporation because we have the addition of that water. And also because the ethyl alcohol is more resistant to the evaporation. So than the isopropyl. So that's the thing is with isopropyl, we used to see that a lot in our hand sanitizers, but it is, you know, more microbicidal, is more effective, but it is less expensive than the ethanol, but its evaporation rate is just screwing it over. So essentially that's that. And vapors from isopropyl alcohol can have effects on the nervous system when you're continually exposed. For oxidizing agents, here we're talking about anything with basically an oxygen product of some kind that would be damaging to bacteria. So this is useful against endospores and other microbes. So therefore we can use this to sterilize things when used appropriately. So concentrated hydrogen peroxide is useful for that. We have oxygen-free radicals that we will be forming. And, you know, some bacteria can't control, don't have any way to heal isn't the word that I'm trying to think of. Some bacteria don't have a way to manage the presence of these sort of oxygen-based products that can be dangerous to the cell. So, right. So these guys, as an antiseptic, if you're going to be using this household, 3% hydrogen peroxide is used for skin and wound cleansing, mouthwashing, and bed sore care. It's going to treat infections caused by anaerobic bacteria. Remember, because those guys are the ones that can't defend against the oxygen products that I was trying to say just a minute ago. So 35% hydrogen peroxide is used in low temperature sterilizing cabinets for delicate instruments that might not be able to be exposed to high temperatures. It's colorless, it is caustic, it decomposes into water and oxygen gas in the presence of light, metals, or catalase. Of course, catalase is the enzyme that bacteria use to break it down when they are able to, right? The aerobic ones. Germicidal effects are due to toxic reactive oxygen being produced and that causing damage, you know, within cells. Okay, so wound cleansing, bed sore care, mouthwashes, we said that already. You can also use this to disinfect your soft contacts, surgical implants, plastic equipment, utensils, bedding, room interiors as well can be cleaned with hydrogen peroxide. You can sterilize using a vaporized form, almost gaseous form of hydrogen peroxide for treating small industrial items and larger enclosed spaces. Ozone has similar effects. It's going to cause similar damage. Think about it the same way that you can with the hydrogen peroxide. Right, detergents, it's going to target the bacteria, viruses, and fungi, but not completely, right? So we can't use these to sterilize. These are going to be our polar molecules that act as surfactants. Anionic detergents will have limited microbial power, while cationic detergents such as quaternary ammonias or quats are going to be more effective as antimicrobials as far as how they're going to interact with you know, the cell membranes and things like that to disrupt all of that. Usually we're going to be combining a detergent with something else. Like when we were talking about chlorhexidine and Hibiclens, we had chlorhexidine combined with a detergent of some kind that breaks down the cells so that the chlorhexidine can get in a little bit better. So that things often function better in combination with these. Yeah, I don't know. So breaking down our cytoplasmic membrane with these guys, these are going to mimic sort of the structure of what we see in the phospholipid bilayer. It's ineffective against certain organisms, so certain bacteria, certain viruses, and it will be greatly decreased its function in the presence of organic matter. Certain quats of the quaternary ammonia compounds we can no longer use in consumer level, but they can use it in hospital settings. All right, so these are effective against viruses, algae, fungi, and gram-positive bacteria. They're rated for low-level disinfection, cleaning utensils, and things like this. you know, what people use detergents for. I think you were aware of this. So surfactants are often going to be used, like these are our quaternary ammonia compounds, okay? So these guys here, these are our quats. Okay, so this is because we have our nitrogen group surrounded by 4 other groups. So this is a quaternary ammonia compound. They have an amphipathic nature, so they've got a long hydrocarbon chain, which is hydrophobic, and then the head, which is a positive charge to it, okay? So there is its little amphipathic nature, and that's what gives it its ability to break down a membrane pretty well. Yeah, doesn't work well in presence of organic matter. We often use these quaternary ammoniums for ophthalmic solutions and cosmetics. So that's going to be like your contact solution, stuff like that. Preservative, they're used as preservatives and microbicides in general. But like it was said earlier, Pseudomonas, which is a type of bacterium, it grows just fine in the presence of this. And it actually can grow quite abundantly in soap dishes where you think that you are, you know, maintaining a clean environment. And these guys are, you know, going crazy about it. So they're going to be more germicidal when combined with other things, essentially. With the metal compounds, we're going to talk about bacteria, viruses, and fungi. We have the heavy metal germicides that contain either an organic or inorganic metallic salt. It just depends. Essentially combined with other molecules, right? So mercury, silver, and other metals will exert microbial effects by binding onto functional groups of proteins and inactivating them. We've talked a lot about the effect of potential effect of metal ions on proteins. So some proteins need them in order to function, whereas others can actually be deactivated in the presence of them. And so that's what we're going on here. Microbes can become resistant. These also can be toxic if we inhale them, ingested, or absorb them. And then some people can become allergic to some of them. So using organic mercury tinctures is a fairly effective antiseptic. You know, we don't think about mercury a lot being something that we're having in our environment around us all the time, but you're by far encountering much greater amount of mercury from your everyday lives and what you're doing with whatever your cleaning solutions could be, or lotions that you could be using, or whatever it is, the contact solution and other foods that you're eating and all of this. You're getting more mercury from that by like a considerable amount than you will ever get if you got vaccines like every day. Just saying. So silver nitrate, we know silver is pretty good for antimicrobial stuff. Silver nitrate can be used as a solution for topical treatment of wounds or as ointment. These, we have the oligodynamic metallic compounds where we have mercury and silver compounds that we can use as germicides, but these can be toxic in very small amounts. So that's a problem with this a lot of the time, and it can also be neutralized by biological waste products as well. And resistance, of course, that's an issue. So with weak organic mercury tinctures, these are effective antiseptics and prevent infection. And we use them in, like we said, cosmetic and ophthalmic solutions. Silver, we use in the form of silver nitrate as a germicide, silver sulfadizine for burn treatment. Pure silver, we can incorporate into actual catheters themselves to give them an antimicrobial property. Colloidal silver, which is just a mixture, essential suspension of silver, as a mild germicide. And then silver ions can be incorporated into hard surfaces and textiles to give them antimicrobial quality. Next are the aldehydes. Most of us have heard of these. So whether we're talking about glutaraldehyde or there's a whole bunch of formaldehyde. So basically these are going to kill endospores and other microbes. These can be used for sterilization when used appropriately. So anything with a CHO functional group at the terminal carbon, that is going to be our aldehyde. So glutaraldehyde can disrupt the activity of enzymes and proteins. And we have OPA, which is orthophthaldehyde, which is another aldehyde, which is going to be a little bit more friendly to people, the use of in people or on people or around people. So because glutaraldehyde is a little bit unstable, especially when exposed to increasing pH or a change in temperature. So OPA, orthophthaldehyde, is more stable and everything like that, but it is also much more expensive than glutaraldehyde. So it just depends on what your application is and whether or not you're going to want to spring for the OPA, right? So glutaraldehyde, broad spectrum, we use it as a sterilant. We use it in the presence of organic matter, of course, and this will sterilize materials damaged that'll typically be damaged by heat. And then we have formaldehyde, which, formalin is the aqueous solution. It's a high level to intermediate level disinfectant, and it is extremely toxic to people. I mean, most of us are aware of this, that the glutaraldehyde is not great, but then formaldehyde is really not good for you. Disinfect surgical instruments, and then we will have it'll be the active ingredient in embalming fluid. I don't know much about embalming somebody. I don't know much about, like, I haven't taken anatomy. I haven't taken human anatomy and cut up a cadaver or anything like that. I don't know anything about these things. So other than, as cleaning agents, that's all my experience is with the aldehydes. But I have watched Mortuary Assistant game. I haven't played it, but I watch other people play it. Sorry, it's not very exciting. That's my story about it. Anyways. That's what my husband wants to do, is be a mortuary assistant. So anyways, orthophthaldehyde, I can't say it, but OPA is how we would abbreviate this, right? It's going to have similar action as glutaraldehyde. It is faster acting, it is non-irritating, but it will not destroy endospores. So this cannot be used as a sterilizing agent, and it's more expensive. Again, it depends on what you're using these things for. Okay, gaseous sterilants. So ethylene oxide is a gas. It kills endospores. Other gases are just less effective than ethylene oxide. It is colorless. It exists as a gas at room temperature. So we use this to treat entire rooms sometimes. It interacts with functional groups of DNA and proteins to block DNA replication, as well as enzymatic reactions of the proteins. Chlorine dioxide is a strong alkylating agent that can be used in a similar fashion. But ethylene oxide is explosive. So it will be combined with a high percentage of carbon dioxide or fluorocarbon before it's being released into being used in whatever area, as much as possible to make it as safe as possible, essentially. It can damage the lungs, eyes, and mucous membranes if contacted directly. So it's very bad for you. It's also a carcinogen, which causes cancer. So this can create what we call a chemiclave, which is chemical sterilization. Put something in a room, fill the room with gas, and then now that's our chemiclave, right? But it is explosive and carcinogenic, causes damage to eyes, mucous membranes, and lungs. And then we have the chlorine dioxide mentioned briefly, which we use to treat drinking water and wastewater and certain food processing equipment. And whenever we're getting rid of medical waste, we can treat that. Yes, and we also used it to disinfect the Senate offices whenever the Senate was attacked with anthrax in 2001. So useful there. Okay, so our acids and our alkalis. So remember, acid is going to be low pH, alkali is going to be high pH. So these are going to affect bacteria, viruses, and fungi. We have organic acids that are going to be used for food production, for treating microbes in food production. And we have pH alteration due to, we're treating with acid or base. So of course it's going to change the pH of whatever you're treating, but that will lead to the proteins and other molecules in the body not being able to perform as usual because we're disrupting the function of those hydrogen bonds that would typically be allowing those structures to function properly. So food manufacturing, deodorants and deodorizers include these. So ammonium oxide, we have our detergents, cleansers, and deodorizers, whereas some organic acids we use in food preservation. This is going to include acetic acid, which is vinegar, propionic acid, lactic acid, benzoic acid, and sorbic acid. You probably heard of some of these, like that vitamin C is ascorbic acid, that we use these as preservatives a lot of time, but they are organic acids. Essential oils actually can be used. They are effective at stopping microbial growth. It just depends on the oil. And whenever there is an oil that has been proven to actually be useful at stopping microbial growth, the FDA can approve those essential oils that do contain extracts that have been proven to work. So that is a thing now. So here are some examples of some products and how they work as far as what we've just learned today. You can look through these and find some of your favorite stuff on here. I don't use alcohol-based mouthwash personally, so I can't say for using Scope mouthwash, but I have used in the past, I've used Listerine, which is, I guess, carbolic acid, the phenol. I don't think it is anymore though, right? It would have been in the past. Now you got me wondering. I don't have it anymore. So I would go look. I don't care enough. Sorry. But I don't think it's alcohol-based anymore. That's what I'm trying to say. I don't think that is. And I use like the Crest mouthwash. I don't know. I'm telling you everything that I use. Like you care. Okay. Just look through these. And I don't know. They kill things. And not everything, right? So anyways, that's the end. That was quite the departure there for a second. I thought I was going to start rambling. I did. I apologize. Why aren't there any methods for sterilizing animate surfaces? So I am going to leave you guys with that one, and that will be the end for me, and I'll see you next time.